This is lecture video 43, and in this section, we will talk about areas of surfaces of revolution. Before we start, I want to mention a real-life example related to this topic first. For example, when you jump a rope, the rope sweeps out a surface in the space around you, similar to what is called a surface of revolution. The surface surrounds a volume that you can see here, and this volume is a volume of revolution, and many applications require that we know the area of the surface of this solid rather than the volume it encloses. Okay, so here we consider this curve, which is kind of like a rope, and when you jump a rope, you do what? You revolve this rope around the space around you like this. So if you revolve this curve, okay, let me put some recall here. If you revolve this curve around x-axis like this, revolve this curve around x-axis, what you obtain? You obtain a surface, and the insider part is empty, right? Because since there is no region now under your curve and you are not revolving this whole region, you are just revolving the curve. That's why you obtain just the area of the surface, not the solid object inside it. So here, my warning is the inside is empty. You obtain only the surface. Okay, what is my recall is if you revolve the region, not just the curve, but the region under that curve. So let's say this is your curve and you are revolving the whole region around x-axis, let's say, then what you obtain is something like this, right? So then you will obtain the whole solid object. Okay, if you revolve the region, revolve not just the curve, but also the region under that curve, this results in solid objects. Okay, so this is the difference between revolving a curve and revolving a region. But if you are revolving a region, the insider part is not empty, but just here you are revolving the curve, the inside is empty, you are just having a surface around the surface of revolution. Okay, so we want to compute the surface area of this surface of revolution. And we will divide, the idea is the following. You divide your surface into circular strips like this. So by dividing the surface into circular strips like this, here, at over each sub-interval, you will concentrate on these circular strips, and you find this surface area of this each circular strip, then we will sum them up to obtain the total surface area. So this is the idea here. So let's concentrate on this circular strip. We want to find the surface area of it. So let's take it to here. It is some strip like this, circular one, and it is more like a cylinder, right? So this is the center, and where it is denoted like that. And as we did before while computing the lengths, we will denote very infinitesimal part of our curve as ds. So ds is here. It is some segment of our curve. So the radius of the circle here is given by our curve, right? It is given by the curve. So the radius is in fact given by the curve. So it is f of x. Radius is like that. And now I can express the surface area of this cylinder, of this strip. How can you do that? You just cut it up and open it up like this. After cutting it, you obtain something like this. And the circumference of it, this part, since the radius is f of x, it is 2 pi r, where r is given by your function, as you can see. This is the function and the radius is given by the curve. And what is this part? This part is the height of it, right? The ds corresponds to the height of your cylinder. So it is here. That's why the area of this strip is given by, obviously, the area of this rectangle, where you denote it like 2 pi r ds, where ds part is the, or you can just write 2 pi r times the height. So r is given by the curve, and the height here is given by the sub-segment of your curve. So it is just ds. Okay, then I think we are ready to state the surface area formula. Surface area is given by, so to cover the whole surface area, we will be continuously summing up all the areas of this little strip. So continuous summation we will do, and we always put integral whenever we want to do a continuous summation. So we will sum by integral continuously the areas, surface areas of all those strips like that. So it goes like 2 pi r ds, where r is given by the curve, and ds is, in fact, you remember what was ds? We covered it in the previous lecture. It is 1 plus your function's derivative square dx. So the formula gets its final form then. It is, of course, the boundaries of the integration is from this point to this point, where x equals a to b, 2 pi fx, f of x, 1 plus dx. So this is an integral with respect to dx now, and as long as you know the formula for your curve, you can just insert it to here, derivative is inserted to here, and then you will try to compute this definite integral. And I also want to remind you that this can be written also in this form. Also, one more recall maybe. Remember the length formula. This is the surface area formula. What is the difference between the length formula and the surface area formula? It was like this, and from A to B, just this part, you know, just this part corresponds to ds. So if you remove these three things in front, just the square root part, then you find the length, but the surface area has these extra terms in front. Okay. If you take just this part, just the s part, it gives you the length, but this corresponds to the surface area. And you can cover the similar story when your function is given not with respect to x, but with respect to y. Here, our function is y equals f of x, okay? Y equals f of x. So the formula goes like this. This is the surface area formula, just like we discovered here. This is the formal statement. F of x, f prime of x, you take the square. So your function y, and the integral is with respect to dx. And the similar setting when your function is given with respect to y, x is g of y. Let's also draw a picture also for this case. This time your curve is this one, where the equation of it is given by g of y. And you revolve this curve around y-axis. So you revolve it around y-axis. Remember, we revolved our curve around x-axis in the previous setting, now around y-axis. After you revolve it, okay, what kind of thing you will obtain? What kind of three-dimensional surface area you obtain? it will be something like this if you revolve around y-axis. Okay. Okay, you obtain this. Now you will look at very thin horizontal strips this time. So this will be your strip that you will be using to sum that you will be using in your summation to cover the whole surface area. Okay, so this time, this is your ds, a small segment from your curve, and this is an arbitrary y point on y-axis, and you see this is the radius of this strip, and the radius is in fact given by the curve. You see, if the image is y, the point where you hit on x-axis is in fact g of y, right? That's why this time the radius is given by g of y function, as this part is the radius. Okay, you do the same. You take this strip, cut it out, open it up, and you will consider the area of this rectangle. Now, the circumference is given by 2 pi r, where r is g of y in this case, and the height, this is the height, remember, is given by ds again, which is a very small part from your curve. Okay, then the boundary of your integration, okay. So what we are doing here is, okay, we take this curve, which was given x equals g of y. Okay, this was the curve. And so on y-axis, it has some boundaries like C and D. Now I will try to write the area of this strip now. It is 2 pi r h height, where r is, in this case, given by this and h is given by ds. Then the surface area is a continuous summation of all those areas of this strip. So continuous summation means that you are integrating it from the point C to the point D on y-axis. So from C to D. R is g of y, and now instead of ds, we will be writing the dy version of it. So it goes like this time, g prime of y squared dy. So the integral in this case is from C to D, 2 pi r g of y, which is the radius, 1 plus g prime of y squared dy. So this part comes from the radius and this part comes from the ds part. And as you can see in this setting, where your function is given x equals g of y, the integral and everything is with respect to y. You are putting the y boundaries and so on. Okay, this is the case for where the integration is with respect to y and you put everything in terms of y inside your integral. Okay, let's apply these two ideas. So the first example, find the area of the surface. Sorry. Let me see which one to solve first. Okay, I think I will write my own example here. Okay, so let's solve our first example, which is an example that we compute integral with respect to x. So the first example is set up an integral for the area of, okay, let me say, find the area of the surface of surface generated by revolving the curve y equals 2 square root of x between over this interval about, we are revolving it about x-axis. Okay, this is the question. So the picture for it will look like, okay, this is xy coordinate. This is y equals square root of x, and we will consider it from the point 1 to point 2. And we are revolving it around x-axis like this. So what you will obtain? You will obtain a three-dimensional surface area like this, right? So we are considering this whole surface area. That's why I am dividing now. I'm dividing it into strips now. We discussed all this story above. Okay, now I will be considering the area of this strip to find the surface area as the integral of this area of this strip. So 2 pi, remember we covered this here. The integral goes like 2 pi RH, where this is the area of this surface area of this strip, where R is f of x and ds is given like that. Okay, so 2 pi, this is R, and square root of f prime x square dx, this is the ds part. Okay, so this is R, this is what ds is. Now I need to compute this part, right? You see your function here. This is your function, that's why the first derivative of it is 1 over 2 times, sorry, there is already 2 there. 2 times 1 over 2 times itself, so these are gone. That's why the first derivative function is like that, and you are taking the square of it. By the way, what are the boundaries for the integral? It is from 1 to 2. Okay, like this. So from 1 to 2, 2 pi f of x is here. 1 plus derivative squared, so 1 over x. Like that. And let's try to compute this integral. You can take this square, I mean, you can do this multiplication now. 1 to 2, 2 pi, or let's write just 4 pi, and do this multiplication. If you multiply x with 1, it is x. If you multiply x with 1 over x, it is 1, right? Okay, how to integrate this? Then we will be using a substitution. If this is your u, this will be your du. That's why this integral can be rewritten as square root of u du, where the square root function is a power function like that. And you also, okay, this is 4 pi. What is the integral of u to the power 1 over 2? It is u to the power, add 1 to the power, divide by the same power, and then you will do your back substitution. So x plus 1 was your u, and then you can insert safely the x boundaries here. Okay, so the result will be 8 pi over 3 square root of this number minus square root of 18, I guess. So this real number, which is a positive real number, is in fact the area of surface of revolution of this type of thing. Okay, let's move on. Let's try to solve this example now. Now we want to just set up an integral for the area of the surface generated by revolving this curve around y-axis. Okay, the question is, set up an expression for the area of surface revolving around y-axis. So since we are revolving around y-axis, it makes sense to write function in terms x in terms of y like this. Okay, x is g of y. Then we will need g prime of y. What is the derivative of 1 over y? It is 1 over y squared. So the surface area is given by this definite integral 2 pi g of y 1 plus g prime of y squared square root dy, where this part is your radius, as we discussed above, and this part comes from ds. What are the boundaries for y? It is from 1 to 2. Okay, let's just set up this integral and stop. So it is 2 pi times your function, depending on y, it is 1 over y. times 1 plus square of this expression, right? Minus 1 over y square dy. So this integral gives you the surface area for the described surface of revolution. Okay, let's solve one more example and then stop. So x is given in terms of y. So g of y is like that. And you are revolving this curve, this pink curve, around y-axis to obtain such a surface area, such a surface. Inside part is empty. And boundaries on y coordinate is from 0 to this number, ln2. And we want to find the surface area of it. So we will divide this whole surface area into very thin strips like this, horizontal ones, and we will consider the surface area of such a strip where, okay, for some arbitrary y, the radius of this strip is given by g of y function. And here, this part is the height coming from your curve. Okay, so the surface area is expressed as the definite integral 2 pi g of y, everything is with respect to y here, g prime of y squared dy. So from where to where, look at y coordinates. The boundaries of y is from 0 to ln2. And now we need g of y function, which is given here, and g prime of y. What is the first derivative of this function? G prime of y is e to the power y is itself times the power, times the derivative of the power divided by 2. So it is, in fact, e to the power y minus e to the power y over 2. Okay, let's insert everything to our definite integral. So from 0 to ln2, these are the boundaries for y. 2 pi times this function, e to the power y plus e to the power minus y over 2, and inside the square root, what we have? 1 plus the derivative is computed here, e to the power y minus e to the power minus y over 2. Don't forget to put this square here, and then you can close square root dy. Okay, so let's do the computation. What is this thing? We need to compute this square. It is, or let's start from the beginning on, 1 plus square of this expression, e to the power 2y minus this multiplied with this times 2, so 2 plus e to the power minus 2y over square of 2 is 4. So what do we have here? If you write over a common denominator, it is 1 plus e to the power 2y over 4 minus 1 over 2 plus e to the power minus 2y over 4. 1 plus 1 minus 1 over 2. Just combine these two, it is plus 1 over 2. So this whole thing becomes like this. And this thing now is a perfect square. It is the square of this expression if you consider that expression. So it is a perfect square like this. You can verify it after computing the square. So the integral is done. Let me continue from here. It is from 0 to ln2, 2 pi, this expression, e to the power y, plus e to the power minus y over 2. So square and square root, they will cancel each other. So e to the power over 2 again, right? dy. So you are multiplying the same thing with itself, in fact. So if you do this multiplication and if you do this simplification first, then you obtain 0 to ln2 pi times, you will just multiply everything here. So e to the power 2y plus 2 e to the power minus 2y dy. Okay, now you are ready to integrate. It is pi, by the way, there is another 2 here, so let's write it here. So pi over 2, how do you integrate e to the power 2y? So we can put a recall here about that general rule. It is itself over the coefficient here in the power. So itself over 2, where 2 is the coefficient at the power, plus 2y plus itself over the coefficient like that. And then you have to evaluate this result at the upper lower boundaries like this, ln2. So the resulting real number will be the surface area of this three-dimensional object. So I stop here. Thank you for your attention.